Hello everyone, welcome to my calculus lecture. In this lecture, we study the chain rule. Let us first consider the function y equals square root of x squared plus 1. Notice that this is a composite function of two functions that are y equals square root of u and u equals x squared plus 1. So we have no problem finding dy by du and du by dx individually. But how do we find the dy by dx? That's the question. It turns out that the so-called chain rule gives us the tool that allows us to find the derivative dy by dx. So this is what the chain rule is about. Let's let y be f of u and u be g of x, right? So in other words, y is a composite function, okay, of these two functions. All right, so if both the dy by du and du by dx exist, then dy by dx also exists, and it is given by none other than dy by du times du by dx, which is also written as f prime of u and g prime of x. Okay, so to prove this chain rule, we're gonna go to my notepad. Okay, so we wanna talk about the proof of the chain rule. Okay, so again, we have two functions, y equals f of u and u equals g of x. So in fact, as a function of x, y is a composite function of these two functions, right? Okay, so dy by dx, that's the limit. So by definition, the limit, instead of h, I'm going to use actually dx. So limit dx, delta x goes to 0, delta y, okay, by delta x, okay. So, the derivative dy by dx also can be given in this form, right? Delta x, delta y, these, represent what? The increment of x, increment in x and increment in y. So now this can be written as delta y by delta u times delta u by delta x. Okay, same thing. By cancel out the delta u, you get the same thing as, this delta y by delta x. So here now limit delta x goes to 0. What is delta y? Delta y, increment in y, in terms of f, that's given by f of u plus delta. When the increment in u is given by delta u, delta y is given by f of u plus delta u minus f of u, right? So f changes from f of u to f of u plus delta u, right? Over delta u. And delta u, okay, so the increment in u, when the increment in x is a delta x, increment in u is given by g. So it changes from g of x to g of x plus delta x. So, the increment is given by g of x plus delta x minus g of x all over delta x. Okay, so that equals limit delta. Okay, so there's another thing I uh, have to mention, right? So by the way, also I didn't write it down, but there's another assumption, right? The assumption is both so maybe I should write that down. So here we assume that both dy by du and du by dx exist. Okay, so y as a function of u and u as a function of x, they both are differentiable. Okay, so these two guys exist. So since du by dx exists, that means when delta x goes to 0, delta u, they must go to 0 also. Otherwise, du by dx wouldn't exist. Remember that? In order for the limit, so actually this guy here, right? This guy here equals limit delta x goes to 0, delta u over delta x. So in order for this to exist, right? You know, when delta x goes to 0, delta u must go to 0 also. So it's gotta be like what, 0 over 0 type indeterminate form, so that actually the limit value can exist. So when delta x goes to 0, delta u goes to 0 also. And then we have f of u plus delta u minus f of u all over delta u times, in this case, for the second part, limit delta x goes to 0, g of x plus delta x minus g of x all over delta x. Okay, the reason we can, and that this previous limit is written by the product of these two limits is that each of them, each of limits exists, right? So this one here, the first one, is none other than dy by du, and by assumption we know that it exists, times this guy here is du by dx. So we just proved the chain rule. So dy by dx is given by dy by du times du by dx. Okay, great. However, I must say something. This proof is incorrect. Okay. Uh, well, I don't know, if I should say like this proof is incorrect. This proof actually, uh, more like, it's not rigorous. Okay, so, I should say, so note that this proof is not a rigorous proof. Well, so actually, I can say that this is not entirely correct. Why? Because delta u, which is g of x plus delta x minus g of x can be zero. Okay, it can be zero, which means that in that case, the dividing by the delta u is problematic, right? It can be problematic if this could be zero, right? If this could be zero. So, this proof makes sense by assuming that delta u is not zero. But there's no guarantee that, delta u is never equal to zero, okay? In general, it could be zero, right? So, the bottom line is, I mean, this proof, gives you some, the idea about, how the chain rule works, but it's as a mathematical proof, it's not rigorous one. Okay, it's not you know entirely correct. So there are like rigorous proofs. So in fact, in my lecture note, I gave like the two versions of rigorous proofs of the chain rule. Okay, so at the end of my lecture slide, I listed the address for the lecture note. Okay, so in case you are interested in, right? Uh, I mean, if you are not interested in, you don't have to worry about that. Okay, that's not crucial. Uh, you know, for most of you, what's important is, the being able to use the chain rule. Okay, but again, like if you want to, you know, study more rigorous proofs, then you are more than welcome to go to my lecture note and delve into that. And actually, I you know the encourage you to do that. Right. Okay, so let's get to my lecture slide. So we know the chain rule, right? Often, like a student, they feel like some kind of difficulty when they, try to apply the chain rule. The hardest part of applying the chain rule is to identify the function u. Once you have, the corrected function u, then the rest is easy. Find the dy by du and du by dx, and you just have to multiply them to get dy by dx, by the chain rule. Okay, so the candidate for u is usually the function inside the parentheses, or sometimes brackets. But sometimes like your composite function doesn't have like parentheses or brackets. In that case, the innermost function, all right, you can most of the time you can easily identify the innermost function, and that's going to be your u. most likely. Okay. So here are some examples. So we are going to go over each one of them. So to do that, let's get back to my notepad. Examples. So the first one, the function is so you find the dy by dx. Okay, so the first one function is given by y equals square root of x squared plus 1. Okay, so let's talk about this first. Right, so in this case, you don't see, this is a composite function, right? Okay, and you don't see like parentheses or like, brackets, but, you can easily identify the innermost one. Innermost one is what? This guy here. The one inside the square root. Okay, so that's going to be our u. So we can write this as y equals square root of u and u equals x squared plus 1. So now next thing, once you identify u, then all you have to do is calculate dy by du. So square root of u, the derivative is 1 over 2 times square root of u. Okay? In one of them, one of the earlier lectures, I asked you to remember the derivative of the square root of x, right? Which is 1 over 2 times square root of x, okay? Because you stumble upon the derivative of square root of x so often, right? You better actually remember that, all right? To save time and energy. So that's what it is. Okay, so we have that. And du by dx, no problem. That's simply 2x. By the chain rule, dy by dx is given by dy by du times du by dx. So we just multiply these two guys, right? So that's going to be 2x over 2 times the square root of u, and we can cancel 2 out. X over square root of u. So you know what? In the end, you want to change a u to, x squared plus 1, okay? Because, at the end, uh, the you want to write down your solution, in terms of x, okay? So that's going to be x over square root of x squared plus 1. Okay? So that's your derivative, dy by dx. It's not bad, right? Okay, so let's talk about the next one. Example number 2. Uh, the function is given by y equals x cubed minus 1 to the power 100. Okay? All right. So in that case, you guys see, the parentheses, right? So the one inside the parentheses is most likely u. Okay. So in fact, the given function can be written as u to the power 100, and u equals x cubed minus 1. So that gives these two guys, right? In fact, the given function y is the composite function, a composite function of these two functions. All right, so now we find dy by du, which is easy, right? That's by the power rule, 100 times u to the power 99. And du by dx, that's 3 times x squared. Also, in fact, in the end, we are going to write down u as the function of x, right? Which is actually x cubed minus 1. So that's 100 times x cubed minus 1 to the power 99. So dy by dx equals, by the chain rule, dy by du times du by dx. So this equals 100 times x cubed minus 1 to the power 99 multiplied by 3x squared, right? So that's going to be 300 x squared times x cubed minus 1 to the power 99. So that's going to be the derivative dy by dx. Okay, so moving to next example. So next example is y equals sine of 4 times x. Okay, in this case again, you don't see parentheses or brackets, but the innermost function can be easily identified. That's 4x. This 4 times x is what? The angle, right? That's an angle for the sine function, right? So that's the innermost function. So in fact, y equals sine 4x is a composite function of these two functions, sine of u and u equals 4 times x. Okay, so dy by du, no problem. We know how to find the derivative of sine, right? That's cosine of u, and du by dx, that equals 4. In fact, we're going to write cosine of u as cosine of 4 times x. Okay? So now, dy by dx, by the chain rule, dy by du times du by dx, which is going to be 4 times cosine of 4x. Okay, that's the derivative. Next example, y equals square root of sine of x. Okay, here one thing you have to be careful about is sine of x can be negative. Okay, sine of x can be negative. So you have to be careful about the domain. Okay, for instance, well anyway, so what I'm trying to say is that the square root function, like the square root function is defined when whatever inside the square root, right, is non-negative, right? Okay, so it can't be, you can't have like a square root of a negative number. So here, the sine of x is required to be greater than or equal to 0. Okay, but like I said, and as you know, sine of x can be negative. So then you can actually restrict the domain, right? So for instance, you can choose x to be greater than or equal to 0 and less than equal to pi. You know that the sine of x is non-negative, so it could be 0 or the positive in the first quadrant and second quadrant, right? So this is 0, pi over 2, pi, 3 pi over 2, and again back to 0, that's 2 pi, right? So you are rotating like counterclockwise. That's something like you learned from trigonometry, right? So that's the first quadrant, second quadrant. In this order because we are rotating. The positive rotation is a counterclockwise rotation, right? That's the third quadrant and fourth quadrant. And so in the first quadrant, or so everybody is positive. In the second quadrant, only sine is positive. Third quadrant, only tangent is positive. And then fourth quadrant, only cosine is positive. Okay, so it's good to remember. All positive, sine positive, only tangent positive, and in the fourth quadrant, only cosine positive, right? So in the first, second quadrant, sine is positive, and including, 0 and pi, this is going to be non-negative. Okay, so in this case, you can actually, as an example, right? As an example, you can choose this as so closed interval from 0 to pi as domain for this function y equals square root of sine of x. Okay, so that's a little detail, but we get back to finding the derivative of this, right? So in this case, again, you don't see like a parenthesis or brackets, but innermost one can be easily identified, which is the one inside the square root. So that's going to be our u. So this function here, y equals square root of sine x, is a composite function of the following two functions. So y equals square root of u, and u equals sine of x. So we find dy by du, which is 1 over 2 times the square root of u, and that equals 1 over 2 times square root of sine of x. and du by dx, that's cosine of x. So dy by dx by the chain rule is given by dy by du times du by dx, which is cosine of x over 2 times square root of sine of x. So that's going to be the answer. Okay, more details of my discussion in this lecture can be found in my lecture note at the following address. Okay, again, as usual, you just have to click on this address, which is hyperlinked, to get to the note. Also, like I mentioned earlier, in case you are interested in, okay, we proved the chain rule, but that's not entirely correct, the proof, okay, right. Uh, but the two rigorous proofs of the chain rule are given in my lecture note at the following address. So this is also hyperlinked. So you just click on it to get to the note. Okay, and also if you want to visit my main blogger site, you just need to click on this blogger, this word blogger, which is also hyperlinked. Okay, so thank you folks for listening and watching my lecture, and I'll see you next time. Bye bye.